Greetings and welcome. This is Artie from Artifact Electronics. In this episode, we'll discuss how to use an electronic load, such as the one you can see. This is a BK Precision Model 8540 with a max power handling capability of 150 watts. I picked this up a while ago on eBay, used. I think they retail for about $450 or $500 or so, but this one was on sale for $200. It was very lightly used. Well, I can't tell exactly, but looking at counting the number of marks on it and just looking for signs of usage, there were very, very few on here. Now, I have briefly tested this with some of my HP bench supplies, and I just kind of ran through the basic function and it seemed to work. And the reason I did that was we obviously need a subject to test with this. And what we're going to test with this is the Lambda power supply that I fixed in the last episode. Now, just out of the box looking at this, we are basically using, or I didn't want to be using two total unknowns to test each other, because that could create some interesting situations. That's why I tested this a little bit with the HP supplies first, to make sure that it wasn't completely bonkers. I mean, we still don't know if it's 100% functional, but it looks to me like it's pretty functional. The Lambda supply, all we could see last time was that it was able to hold a voltage, but I didn't load test it. And that's because I didn't just want to slap a 50 watt resistor on it and just see if it could crank, if it could generate current. And I wanted to do more than a go-no-go test on it. And with this electronic load, we can actually see what the particular numbers are. And we can also test it in three different modes. The electronic load can test or can be set to one of three modes. The first one is constant current, and the names are pretty descriptive. You set a current and you can monitor how well that current, how stable that current is when you vary voltage against it. The second mode is constant voltage, which is the opposite of the first. You set a constant voltage and then crank the current and see how well it holds the voltage. And the third mode is a constant resistance that essentially places a purely, as far as the generator is concerned, places a purely resistive load in its path, so we can see V equals IR in action. So this is the setup. The Lambda is running through this power strip, through the kilowatt, and the reason I have this hooked up is I want to monitor the power usage, or just a bunch of parameters of what's going into the Lambda, especially current, which we'll get to why. But so here's the setup. As I played around with some of the HP supplies, I was being lazy and just used these call them medium duty alligator clips to connect the voltage source to the electronic load. And after a while it started to generate a lot of smoke. Fortunately, it didn't come from the Lambda, but rather from the other end of the cables here, as you can see, because the wire gauge is obviously too small. It melted the insulation, caused a horrible smell and some unpleasantness when I saw a lot of smoke starting to emanate from back here, where the output is. But all's well that ends well. It was only these cables, so first thing that I did, I built myself some heavier duty cables here with thicker gauge wire banana clips on one end and proper lugs on the other end that screw in. So we should be all set to go. So let's get started by monitoring our line voltage, which is 120 volts, which is normal. The first mode of the load I'm going to use is constant current, which we select using the mode button, and these three enunciators will show us what mode we're in. Second thing I need to do is when this device boots up, it basically limits the current. It has an upper limit on current of 3 amps, and it will always boot up in that particular mode, but what you can do is shift it to 30 amp mode, and next what we need to do is, since we're in constant current mode, let's select the current value, and that we can do, we select the digit of the parameter that we set. Oh, it's already in 3. Now if we turn it up, we can turn it down. So, wow, let's get started with 5 amps. And going into the general vicinity of what we want, I think I want to start with 5 volts. Oh, it would probably help to turn this guy on. And another thing is this is currently in passive mode. It is of course powered up, but the load is not enabled. And the upper display will show us the voltage potential at the input terminals, and the lower value will show us the current. Since it's disabled, there is no current. Another thing we're going to do here is switch this to show us the current being consumed. And right off the bat we can see that the idle current that the Lambda is consuming is 1.2 amps, and we know that linear supplies aren't very efficient, generally between 40 and 50%. Another thing that the kilowatt will tell us is what is the power factor. So currently 60 hertz. The power factor is 0.32, which means it is 32% efficient, or in other words, it's wasting 68% of the power that's appearing at its input terminals. So it's actually lower than the general average for linear supplies, but that is to be expected. The Lambda is about 45 years old, and if you watched the last episode, you saw it had the 6 large capacitors in there. I measured those, and they were slightly degraded in that their values had gone up on average by 8%, but their ESR values had on average quintupled, gone from 0.01 to 0.05. So 0.01 being an expected value of the capacitor that was in there, and all of what that is going to do is it's going to cause it to be yet more inefficient. So it's kind of expected. But one of the main reasons that I do have the current monitor, I will be current monitoring here, is that I'm using standard residential AC outlet. That is has a current rating of 15 amps. Unfortunately, I don't have anything else available unless I ran an extension cord from the kitchen into the basement from the refrigerator outlet, which I think is 20 or 25 amps, but that would probably not be a wise thing to do. So what we need to do is monitor the actual current draw over here, so we don't make fuses blow and things go up in smoke. Okay, then we're ready to test, and let's just remind ourselves we've set it to 5 amps. We need to make sure that the current limiting on the Lambda is higher than 5 amps, because otherwise it won't be delivering 5 amps. And now all we got to do is enable this. What we see, we got 5 amps flowing. Our voltage dropped a bit, which is to be expected. All we got to do is adjust it, and it's sitting there holding it. Now have a look at the power factor. just dropped to 22%. It's for the same reason as I explained before, because of the age of the Lambda. And but yes, it does become essential now for me to monitor the input current to the Lambda. So it is drawing. Remember, the idle current was 1.2 amps, so it's drawing current pretty close to what it's outputting right now. And we can test that by stepping up gently to 10 amps. So we select this digit. And it's not drawing 10 amps. Why? Because the limiter on the Lambda is preventing it. We got to turn that up, and now it is drawing 10 amps. The voltage dropped a little bit, but we can easily adjust it and see that the Lambda is holding the voltage. So we got 5 volts at 10 amps, which we all know is 50 watts. And when we switch display modes on the Lambda, it will tell us what the current consumption is and what the current setting is that we gave it. This is not the actual current in this setting, but actually what we selected. Go back to the previous mode, it shows us actual current and voltage. It is now drawing 9.4 amps AC, and as we can see, that current draw is closely following the current output here. So we are not going to be able to hit 25 amps with this. I can tell you that right now. But you know, let's go and see how high we can go as far as current is concerned. I'm still keeping the voltage low for the and the reason for that is that if I have a higher voltage, we're going to run into the power handling limitations of this at 150 watts. But we'll try that. But first, let's see how high we can go with our current. So let's go to 15 amps. And again, we're not getting 15 amps because the current limiter is on. So now we got 15 amps. And we adjust the voltage again. And we all know that this is 75 watts. And there you go, 75 watts. Now, fortunately, at this point, the AC current being drawn is starting to lag behind the actual output current a bit, giving us a bit of headroom. It's not enough headroom to hit 25, I'm pretty sure, but while we're at it, let's just continue and see how much more current we can measure. At 18 amps output, well, it's not really putting out 18 amps. I'm increasing the current limit again, and now it is outputting 18 amps, and it's drawing 13 amps, and we are getting somewhat uncomfortably close to the AC outlet's current capabilities. But let's see if at least we can get 220 amps. Oh, and I should do my scientific wire test. They're getting noticeably warm, but not uncomfortably so. So we're okay with those cables. So back. And 20 amps. And now we have 20 amps at 5 volts, which should be 100 watts. It is. And we're drawing 13.82 amps from the wall. And yeah, as much as I want to, the devil's speaking into my left ear, says go turn the current limit up some more. I'm not going to do it. I'm just going to have to be happy with it, seeing outputting 20 amps at 5 volts and being able to hold that steady. I'm just kind of afraid that I'm going to hit a certain threshold, and the current coming out of the AC outlet is going to jump all of a sudden. Yes, I know there's no reason for it, but stranger things have happened. So as far as measuring the current, this is where we're going to stop. We can see that the meters, the analog meters, correspond very well to what we've set up, but so far for high current. We disable it, and now let's see how it does with a little bit of a higher voltage. Again, we need to be extremely careful with the current in this case. So let's get up and relax the current. Well, not that much, but let's do 2 amps, because what I want to see is how we're going to do when this outputs maximum voltage. Maximum voltage on this should be 36. Okay, 36 and a quarter about is what it hits. That's actually pretty impressive, because the Lambda is calibrated from the factory to 36 volts, and after the repairs I did on it and its age, it has kept that calibration. So we know that at 36 volts we are going to see 72 watts at 2 amps. So here it goes. Yes, it does. The voltage droops a little bit again, but we got 2 amps at 36 volts, and as you can see, the current is kind of what we expected before. Now we can probably step up the current by another amp without killing anything. And there it is, still holding the voltage. Now, as you can see, we're running up against the limitations of this, because we're already drawing 108 amps, 108 watts, so I can't go much higher than that. But I hear the curious of you saying, well, what happens when you hit that? Will this thing turn into a fireball? Well, let's see. I'm going to keep it in this mode where we can monitor exactly what I'm setting the amperage to and what power is being consumed. And remember, 150 is our limit. Okay, we're at 4 amps now. Let's do a brief check on the voltage, which is being held well enough. And there's our limit. What happens next? Come on. Okay. So it cut itself off because we exceeded 150 watts. I think OPP means over power protection. I need to interject that the manual you get with the BK Precision is anything less than comprehensive. It's about 12 pages that pretty much tell you that if you hit this button, then this light will move from here to here. So it's not going to teach you or attempt to teach you anything about this. It's just a dry how to operate this thing, and there's no theory involved in it. But anyway, I think these two tests, and well, let's bring down the current here so we get it out of protection mode. It worked well at 4 amps, and what it did, it automatically disabled itself. So I'll enable it again, and we can see that basically at 4 amps it's holding at 144, and the voltage, it's holding the voltage too. So with the limited power we have coming out of the wall, and the limited current out of the wall, and the limited power we have in this, that's as far as we're going to be able to go with our constant current mode. But I think both instruments, I think both the subject and the electronic load passed this test. Again, note the meters, they're still pretty accurate, 36 volts and 4 amps over here. Next, we're going to test the constant voltage mode of the load. The constant voltage mode is similar to the constant current mode, except that, and you guessed it, we now set the voltage value that we want to hold at. So let's go into our settings, and 5 volts is good to start out with. Basically, let's just give it a squirt of current here, keep the voltage low, and see what happens. So we enable this, and well, it can't hold the voltage at 5 volts because it's not outputting 5 volts. So we gently start increasing, and when we hit 5, it starts drawing 3 amps, and that's what this was set to. And we can now alter the amperage here, and we can see that it's holding the 5 volts. Let's see, so we could probably, and it won't draw any more current than that at 5 volts, but in the range of adjustments we are allowed for the current, it's holding the voltage perfectly. Now we can turn up the voltage, and to a certain extent it will keep it at 5 volts, even though we are turning it up here. And let's just turn it up a bit and see what we got it to. So we got the voltage set to around 10, or between 10 and 12. It is holding the voltage properly, and altering the current keeps the voltage in the place, at the proper value. Now, you probably also want to know is what is the actual voltage set at here, and the way to find out about that is to disable the load, and we can see that it's actually outputting 10.35 volts, but when we enable it again, it switches right back to 5 volts. So I guess it passed this test too. And again, I don't want to wildly turn the current knob here, because before you know it, you're going to have this thing beeping at you or smoke coming out of the outlet. But I think it shows that that part is working well, that this can even though the voltage on this is set to higher, it will maintain the voltage that the load is particularly drawing from it just fine. Now, one thing you may hear, or you may have heard before, is there's an angry buzzing sound, and that's coming out of the Lambda. And we heard that increase a lot when we were doing high currents. That sound is coming from the dual transformers, and my guess is that the reason we're hearing that sound is because of the rust that was on the outside of the laminates, and I'm afraid that some of that rust has crept in between the laminates, putting irregular spacing in there and not letting them fit together flush anymore. And that's why what you're hearing is a 60 hertz buzz, and the more current we put in, the more we excite the transformers, and the louder they buzz. So just for grins, let's go to 5 amps, and everything seems to be working just fine. Disable this again, and on to the next mode. Our third and final mode on the load is the constant resistance mode that we'll go to. And as the name implies it, we now get to choose the resistance, the pure resistance value of the load. And that's set to 10, nice round number. We have 10 ohm resistor, and we got 10 volts on it. So take out your calculators quick before I turn it on. What kind of current should we be drawing? Time is up, and just as expected, it's drawing, well, a little less than an amp, but that's because the voltage drooped a bit. But we bring the voltage up to 10, and it's drawing exactly an amp. So as we bring the voltage up, the amperage is going to go up accordingly. And as we bring the voltage down, the amperage is going to decrease appropriately. So this would be almost exactly the same as what I mentioned before. If we took a high wattage resistor of known value and placed it across the outputs, that's the way this would react. And except now we have the convenience of having that resistor housed in here, and we can actually adjust it, running at 2.5 watts with 10 volts coming in. And that's what this mode is for. It is more specialized. You will probably most likely use constant current the most. I think the order in which they're presented here, current, voltage, and resistance, is probably a good indicator of how frequently, under normal circumstances, you would be using these modes. And so the third test has also been passed by both devices. So let's check something that's a bit more mundane in nature, but is something that this will also handle well, and that is a regular AC adapter. This one is rated at 9 volts with maximum output of 350 milliamps. And I'm using this one because conveniently the ends are snipped off. And so I'm going to plug it in and connect it to the front of the load. Alright. So we also need to plug in the Lambda directly. Actually, we don't, because we're not going to use the Lambda. And we'll just clip the leads, the output leads of the AC adapter on here. It's in here. So let's go. Alright, so first, immediately it'll show us the no-load voltage, which is always going to be, the cheaper the adapter is, the more significantly higher the no-load voltage is going to be on it. That is to be fully expected. I do get inquiries from friends who are horrified because that go like this. Hey, I have a Casio and I just measured the power adapter before sticking it into the keyboard, and it was supposed to be 9 volts, but it's showing me 14, and I assure them that in most cases it is perfectly normal, and that they should probably go in and measure the actual voltage while it's under load. But then of course I have to explain how to open up the machine and what contacts to probe and so on and so forth. So I think it was enough for those inquiries I got to just tell them that you're okay. And here's of course the proof, and I hope you are watching, you know who you are, that the no-load voltage is significantly higher. And also keep in mind, this is a linear supply here, not a switcher. On a switcher you would see a lower no-load voltage. Then again, on some switches you won't see any voltage because they won't output anything when there's no load. But for now, using this common linear adapter, let's go to constant current mode. And what we are going to do first is basically say, alright, this thing's rated at 350 milliamps. Let's draw 350 milliamps and see what happens to it. So there's the current that we're looking for. It's going to revert back, and on we switch it. So now we can see that at a constant current draw of 350 milliamps, as shown here, it is actually outputting 8.78 volts. And again, that's kind of to be expected. I mean, I would have expected or hoped for at least for it to be able to put out a little bit closer voltage, that the voltage it outputs at max current is a little bit closer to the rated voltage, but that is good enough, because mostly these guys will power something that have a 5 volt regulator in there, and a 5 volt regulator will function perfectly with 8.77 volts input rather than a full 9 volts. So now the interesting question is, what happens if we go in and we increase, or I should say decrease the current, the constant current we're drawing. And I'm going to decrease it in steps, not increase it. And, well, this mode's kind of boring because all it's telling us is that it's actually drawing as much as I've selected. But if we let it switch back, now we can see that at 250 milliamps, it's actually outputting 9.7 volts. And as we can see, so on and so forth. We go to 150, 1094, and most likely if we go to like 75, which is halfway from open load to where we are here, we should probably be somewhere in the neighborhood of 12 volts output. And to do that, we need to go to 75 actually. So when drawing 75 milliamps, dead on, my guess was right that it's outputting 12 volts. So you can see that the voltage versus current curve for these things is it's pretty linear, and it pretty much runs at around 45 degrees on a graph, whereas, you know, ideally we would expect it to be a straight line as far as the output voltage is concerned, but in the real world this is what happens. The next test, we'll just try to do this in constant voltage mode to exactly determine at what voltage will this output, or at the specified output voltage of this, how much current will it supply. And we could do a lot of hunting in the constant current mode to find that, but this one will do it for us, because now we'll just go in and tell it, hey, this thing is a 9 volt supply. So we set the constant voltage to 9 volts, and then we just turn it on. And it pretty much tells us that at 312 milliamps, it outputs the rated voltage. So that's an easy way for you to have a look at the common wall warts and kind of do a performance test on them, even though on most of these you can do your test and see if it can at least deliver the maximum amperage and how much the voltage, or what the voltage value is at that point, to make a determination if the adapter is good or not. But keep in mind that the wide variety of voltages you saw coming out of this thing are perfectly normal. Alright then, looks like both the load and the power supply work, and work well. Obviously I can't do max testing on the power supply because I would need a load that has a capacity of about 900 watts or higher, which is 6 times, which is this thing, the power capabilities of this multiplied by 6. So it's not going to happen right now, but hey, we never know what the cat'll drag in next week, and maybe something bigger will show up and we can finally do a full load test or a full output test on this. But for now, I'm pleased by its performance. It works really well, and that's going to be good enough for now. I hope this episode would have taught you something about an electronic load and help you decide whether you need one for your bench. Thank you for watching, commenting, thumbs upping, and subscribing. And we'll see you next time. You may have noticed that this looks a little different than it did the last time you saw it. And that's mostly because I tried to get rid of all the stickers and stuff like that in front. But I think I got overzealous when I was removing the stickers. And the rack started coming back in a dark gray color when I was trying to get rid of this sticker. And it looked really horrible because there were areas of the gray paint that had the silver showing through, and it was pretty messy looking. So anyway, what I did was I taped it off and I used some acetone on it, and 2 seconds later, I mean, the acetone really took that paint off like it were dust. But it looks a little asymmetrical, but it's very personalized. If it ever gets stolen, I can tell the police that this is the only Lambda with the asymmetrical gray bar up front.